Hello guys, welcome back to my channel Gamma Di Gamma. It's been a really long time. I tried to keep a frequency of a fortnight, that is 15 days between videos, but I can't really explain how bad this semester has been for me in general. Uh, so here's the deal. I'm gonna continue with the Laplace transform streak that we had, and I will also record material from my talk at the math club at Cornell University, because many people in the comment section actually wanted me to sort of could not attend because they're not Cornell students or whatever reason, and they wanted me to record. So I will gladly do that for them, and more information about that soon. But I'm glad to even share my notes or handouts to people who need them. So let's get started with Laplace transform. So to kind of recap what we actually ended up at, we built up a motivation for the Laplace transform from the modified Fourier transform. And this is sort of a recap that I'm gonna do here. It's been so long I've actually forgotten some of the settings I use for recording videos. But anyways, for Laplace transforms, we had one common feature, or you can sort of call this causality, because if you assume we're working with functions of time or time signals, then you can't really have a signal before time zero. All the signal production starts from time zero. So the signal is always zero for t less than zero. Call this causality, call this something. This is an important criteria for the convergence of the Laplace transform integral, because we defined the Laplace transform, capital F of S. I'm underlining them to just denote that they're complex variables having a real plus I times an imaginary, or I, so x plus iy, where x and y are real. That's what a complex number is. Hope you know that. So we define that as this dt e to the negative st f of t. So the I omega from the Fourier transform sort of gone away now, because we've rotated our entire plane by 90 degrees by absorbing the I and omega together and making it into a complex variable s. That's what the modified Fourier transform was, just making omega complex. Multiplying with I just rotates the entire plane. And we had a concept of a region of convergence. I'll give some more examples in this video as well for what that was. That is a restriction on S such that this integral converges. So we don't really want the real part of S to be negative in the exponent like this. Otherwise this integral won't really converge. I mean, even if you sort of integrate, find the antiderivative, the antiderivative won't really, the limit at infinity won't exist. It might blow up. So we don't really want that. Otherwise the Laplace transform does not exist. So I'm going to talk about the region of convergence a little more in this video. And the inverse was 1 over 2 pi I integral on the Bromwich contour, or say Laplace contour, ds e to the st f of it. This is an integral in the complex plane. So a nice way of doing this is by sort of building up a contour that has common elements with this path. So this path is a vertical path because we've rotated all of our plane by sort of incorporating the I omega together. So this is what the contour looks like. But since it's a contour in the complex plane, where this is, say, the imaginary axis, and probably this is like the real axis, we're going to want to sort of close this up as a contour. And we're going to have to take different cases. This is for t greater than 0. And this is t less than 0. We have arrows for orientation. But this is what the entire idea is. This is how inversion looks like. And we place this, everything's connected. We place this according to the region of convergence, because the region of convergence is a condition on S, the real part of S, more precisely. And the real part is basically these values. So that's the region of convergence is going to tell us how far out or how close in can we place this Laplace contour, this Bromwich contour. I hope that sort of jogs your memory about this. And again, as I said, the complex variable s is, there's a real part to it, plus I times another real part, and which I times whatever is that makes it the entire imaginary part. The imaginary part on this contour is obviously going from minus infinity to infinity because we're extending out vertically. The real part of S is sort of fixed by the region of convergence criteria. Okay, usually what's going to happen is if we have a condition like this, the t less than 0 or this sort of shaded region out here it's not gonna have any poles. So by Cauchy-Goursat, the integral is gonna become 0. That's what the idea is. And of course, we're taking the radius of this outer dashed circle to be infinity. So the radius goes to infinity. That's how the closure works. That's how all this entire contour integral is equal to just the integral along this path, because the outer parts go to 0. Although we can only know we've only proved through all complex analysis that, like, let me probably change color here, that this segment goes to 0, just this one. We have to make a special argument for this protruding section. I will do that in like a separate video, which I call probably like the appendix or something. Okay, if we have all of this, we still have to work out some details about the delta function. Why is the delta function so important? Because if we are working with a continuous basis, and we're usually working with integrable functions, maybe not square integrable, but integrable functions whose integrals converge. Otherwise, these integrals, the Laplace transforms, don't exist. And the delta functions form a basis in the infinite dimensional vector space of integrable functions. So I'm just going to call them, say, fancy L. So this vector space is infinite dimensional, so it's sort of like a continuum. Instead of E1, E2, E3 as basis vectors, you have every real number as a basis vector. So when I write f of t, this is actually the component of f in sort of the direction or the base or the basis vector t. This is actually the dot product between f and the basis vector t. Maybe I can put this is a bad notation. Dirac notation works nice here, but we're not gonna like do that until quantum mechanics maybe. So okay, they form a basis. So we really need to care about how we're going to define these guys in Laplace transform. We know how to do them in Fourier transforms. So if you have something like this, in Fourier transforms, we knew what this was. Just by definition, e to the minus I omega t minus t naught. We proved this. You can check the previous videos for this. Now, assuming you have the Laplace transform of a certain function, instead of going from 0 to infinity, let's go from negative infinity to infinity, because we placed the condition that the f is 0 for negative time, so it doesn't really matter here. The negative part is just 0 anyways. Say dt prime e to the minus s t prime f of t prime. Fair enough, that's just the definition of the Laplace transform. The inverse for this is 1 over 2 pi I Bromwich contour integral ds e to the st f of s. And you clearly see why I am having a t prime here and a t here, because the independent variables of integration. That matters because I'm going to club these together. So you see f of s here, I'm going to pull this into here. So I'm going to plug that in the formula for f of t. This is like essentially the steps that we did for finding such a formula for the Fourier transform. Just plugged in the transform in the inverse. So we're going to have a nested integral like this, dt prime e to the negative s t prime f of t prime. What else? Well, nothing much to be done. Everything that does not depend on the integration can really come out. And of course, we can, as always, shamelessly interchange the integrals, because that's totally fine, right? So dt prime f of t prime, nothing else. We have to use the s integrals later. So we have 1 over 2 pi I ds e to the s t minus t prime. This is f of t. And by comparison, or the definition of the Dirac delta function, this guy has to be the Dirac delta of t minus t prime. Otherwise, you won't get this. This is just the orthogonality in the infinite dimensional vector space of integrable functions. That's why all of this matters so much. Just because an inverse exists all the time for any t, as long as the functions are integrable. Otherwise, forget about having a Fourier transform and then having an inverse. This is essentially linear algebra. You need to have the matrix invertible. That's exactly what this is. So it's kind of easy to now see. Gather terms. This is 1 over 2 pi I Bromwich integral ds e to the s t minus t prime. I may forget the dash sometimes because it's like tedious or like takes some time. Sometimes I'm lazy, but it's there. It's implied sometimes. So fair enough, we have a definition for the Dirac delta. Now, one interesting thing I would like to show you is, assuming you have some, let me draw the complex plane again, just to prove a point. Well, assuming you have like a Bromwich contour like this, or just this region of integration, this line of the strip of integration, and S has a real part and an imaginary part, which I will write it like this. Okay. Now, assuming the region of convergence were such that the real part of S sort of, I don't know, 0 belonged to the region of convergence. Maybe that's a better way of putting it. So 0 belonged to the region of convergence. If 0 belonged to the region of convergence inequality, which means we can literally just move this strip around in the complex plane as long as it's in the region of convergence. It doesn't matter how far, as long as it's in the region of convergence, we can totally do that. So assuming 0 is in the region of convergence, I can totally write this. I know why can I do that? Because I'm going to take this entire big closure. So it's going to end up covering all the points that I could not cover before. And the answer won't change because that big closure is always going to contain the residues that we need to invert properly. So that means I can literally write this as imaginary axis, real axis. Nothing changes there. But I've totally pushed this over here. So now we have this. It's coinciding with the imaginary axis this way. And that means that my S on this strip, the real part is 0, right? Because it's on essentially the imaginary axis, which has real part 0. So 0 plus I times, let's say it's omega. Let's call it omega. This imaginary part, let's call it omega. That's what omega was, just a phasor. We have this, and if we plug this back into the definition of this this Dirac delta function here. So we have 1 over 2 pi I integral. Well, if we parameterize ds is I d omega, you make the appropriate changes everywhere else. So we have integral from minus infinity to infinity, because that's the range of omega. Ds is I d omega. Omega has to be real now. E to the omega, let's say I omega, t minus t prime maybe. The i's cancel out. Omega is real. 1 over 2 pi I integral minus infinity to infinity d omega e to the I omega t minus t prime. This is essentially the Fourier transform definition of the Dirac delta function. So what's this? What is this saying? This means, so what's the Dirac delta anyways? Dirac delta is what happens when you have inverse of Laplace acting on Laplace or vice versa of a function, and then you evaluate it at a real part of s equals 0. As long as we can do this, for some this is not possible. If we can do this, this we just showed becomes the Dirac delta definition of the Fourier transform, which is essentially this of the same function. So think of these as different bases. What we've just shown, that the basis vectors in the Laplace transform bases are related to the basis vectors of the Fourier transform bases by just setting the real part of S to 0, or having a region of convergence that contains 0. So this is the conclusion. Since this is linear algebra going on, if this holds true for the basis vectors, it also holds true for the transform themselves. So what's the conclusion? The conclusion is, if 0 belongs to the region of convergence, then Fourier transform exists, right? Because we can totally isolate this omega out, and omega is real. So modified was just a trick. Modified, we don't really work with modified because we have a thing called Laplace. The original Fourier transform exists, and Laplace transform equals Fourier transform. So what I'm trying to say is the Laplace transform is a little more general, because it has S as complex. So it sort of accounts for the cases when, this can't be placed on the imaginary axis, and it can't really become I omega or something that's purely imaginary. But a Fourier transform is a special case of a Laplace transform when 0 is part of the region of convergence, which means when we can literally place this here. As long as 0 is, we literally can. So that's when Fourier transform exists and is equal to Laplace transform. Else, Laplace transform will only exist and the Fourier transform won't. That's the entire idea. That's the entire connection between these things. This is a really, really powerful idea. And this just answers so many questions that people have. People on Stack Exchange, they learn these things. They don't know what they do. They're just formulas to them, and they're like, well, when do I use one? When do I use the other? In physics, usually we use Laplace, we use Fourier transforms. Things aren't as complicated. The inversion is nice. The geometry in the complex plane is a little harder to do. That's why we stick with Fourier transform. But Laplace transforms are literally the most powerful thing ever. Now, a few examples that I will give you are f of t, if it's say 0 and 1. 0 when in the negative region as we want, positive here. Let's find Laplace transform. 0 to infinity dte negative st of 1. Simple. This is the easiest integral. This is like the gamma of 1 or something, minus 1 over s e to the minus s t. Now, before you're hasty, remember this is complex. So s is s real plus s imaginary, which is I s sub I. Now, in the exponential, we have a product. The sum becomes a product, e to the real negative, say, t. Now look at this, e to the I whatever is always going to be an angle. It's always going to have magnitude 1. So as t goes to infinity, it's just going to rotate wildly. The only thing that controls the magnitude now is the real part, is this guy, the magnitude controlling part. So we really need to worry about this. We really worry about the convergence of this. At 0, no problem, it's just 1. What about infinity? For infinity, as long as the total power in front of t is negative, we're fine, which means we want the real part of s to be greater than 0, because if it's less than 0, it will put a positive sign net, and then e to the something positive will never converge at infinity. So we have this condition. So the region of convergence, and I said the region of convergence was a condition on the real part of s. Is the real part of s greater than 0? That's the region of convergence. Keep this in mind. We always need to write this. Make it a habit to write this every time. Which means if we sort of impose this condition, we can go ahead, proudly write this as at infinity it's 0. At 0 it's 1. So we have 1 over s as the Laplace transform of 1. And now, how do we know if it's valid? Well, just invert it, right? Inverted, you should get the same piecewise function. So just use the formula. Just go step by step. We literally know, we have the theory to help us. We're not working in the blind. So where do I place this Bromwich contour? Well, look at the region of convergence. It says real part of s greater than 0. So just draw the complex plane quietly. Imaginary, real. It says this is the complex plane for s, because that's the variable of integration when we're inverting rather. So the real part of s is greater than 0, which means we can't really cross 0. We can't really place our Bromwich contour at 0 or beyond 0. So forget about a Fourier transform existing. You can clearly see from the denominator that it won't, because if you sort of try to do this on a regular contour, the singularity is going to lie on the path on the real axis. So it's going to cause problems when we're integrating in the real space. So complex analysis is the way to go, which means the Laplace transform has to exist. Fourier transform will not exist. Okay, how do we close? Well, idea is simple. Close like this for greater than 0. This is of course because of the lemmas we had for the closure. Close like this for t less than 0. So let's do the greater than 0 case first, because that's the juicy, that's the most important one. Well, notice in this function there is a pole at 0, and that's probably why we couldn't cross. See, if there's a pole, you don't really cross. So the region of convergence also tells you where there's a pole and where you shouldn't cross. It's sort of like the Laurent series. You sort of can't really cross. The region of convergence is confined before the pole. So this ties up nicely to the idea of analyticity and Laurent series that we had before. So the closure we're going to have is going to contain the pole at 0, the simple pole at 0. So which means the contour integral for this big part. So integral over L is now just the contour integral because the closure bit goes to 0. Is just 2 pi I and the 2 pi I from before. Sum of residues, the residue is only at the origin, so just evaluate that. We have e to the 0 t, that's 1, everything's 1. It's just 1 for the positive. What about the less than 0? Well, there's no pole here. The exponential will not cause problems. 1 over s, that only had a pole at 0. If we're here, no poles there. So Cauchy-Gursa simply says that an integral will go to 0, no questions asked. Nicely. So f of t is a piecewise function. We can split it up. It's 1 for t greater than 0, 0 for t less than 0, which is essentially what we had before. So you see this beautiful theory here? Beautiful theory. Too good. This is a cheat code. People, they don't teach you about the inversion, but this is why this is important. It's why complex analysis rules and life is beautiful. I will probably do one more example, or maybe I just can briefly talk about something and then do that example. It's this e to the negative alpha t. If you have a decaying function with a graph like this, of course it's 0. It's 0 when t is negative. That's the unsaid assumption we're going to have from now on. Then the region of convergence for this guy, so this dotted line is going to be the limit or the region of the boundary of the region of convergence. So the region of convergence is going to be sort of this entire thing till infinity. I just placed a contour here randomly. But we can't really exceed this line, whatever this line is. But only for decaying functions like this are we going to be allowed, like the 0 is going to be in the region of convergence, which means from the observations before, the Fourier transform exists and Laplace transform is equal to Fourier transform. Just the difference of like s and I omega, which can be accounted for. This is for a decaying function. This kind of makes sense because the integral does not really have a problem in converging, right? So it's just gonna permit those positive values. But if you have a function like this that's exponentially growing for positive t, something like this, then we have to sort of have to be a little more strict with the region of convergence, in the sense that, say we have some alpha here, some real part of s equals alpha, that's going to be the boundary. Region of convergence is going to be like all the way till infinity from that boundary. But in this mess, we can't really go to the imaginary axis. We can't really go to the real part of s equals 0 because we're restricted by this alpha line here. So that means Fourier transform does not exist. Laplace transform does in the specified region of convergence here. So these are general observations. You can see, so since it's exponentially growing, the convergence is an issue. So we have to impose some conditions that like s cannot really exceed alpha, or at least the sum of them has to be less than 0. That's what's going to happen. Okay, so maybe I'll just do like a small quick one here. So this function is a little less trivial compared to before. So this looks like the solution of an underdamped simple harmonic oscillator with maybe not a decaying term. It's a growing term, so it's probably like an inverse Hooke law, where it's not negative kx, it's positive kx, but whatever. So there is the oscillatory response, that's the cosine term. has an exponential envelope on it. So to graph briefly, if I have the envelope like this, cosine's gonna grow exponentially. That's what it looks like. A pretty neat function. So just find the Fourier transform, sorry, Laplace transform of this. Or cosine omega naught t. Well, what we can do, simplify or sort of just decompose the cosine into the exponential definition. So we have 1/2, the factor goes out, e to the I omega naught t plus e to the negative I omega naught t. But these guys won't really contribute to the magnitude at all. Won't really affect the convergence. These are just I something, e to the I something. They're just phases in the complex plane. So what's really going to affect the magnitude is this, the real part of S. If you decompose everything, so this negative real part of S, because we have a negative sign, plus alpha, all of this we want, I believe, less than 0. So we want anything that's in front of t, the coefficient of t, to be negative. So that means real part of S minus alpha greater than 0. A real part of S greater than alpha, that's the region of convergence. Box it and keep it in your mind. And then just go ahead with your calculation. So this step is really important. Just do it before your calculation. That's my point. Well, you do this. I'm not gonna spend too much time. You get S minus alpha naught over S minus S1, S minus S2. Well, S, anything that's S is complex, where S1 is I omega naught plus alpha naught. S2 is negative I omega naught plus alpha naught. So I'm going to writing this in this form so that it'll be helpful later when I'm taking or finding the residue, when I'm inverting, because I want to check if this is correct or not. So again, place the contour in this region of convergence. So the vertical strip in the region of convergence, and then closure this way for positive t, for negative t. Notice we have two poles here. The poles are on the imaginary axis. Well, not quite, I think, because like alpha naught, they have a real part of alpha naught, and the imaginary part is I omega, I think. Yes. So I omega naught minus I omega naught. This is the strip of real part of S is alpha. Region of convergence is here, basically anything that's sort of like in front of alpha. This entire thing up front, in front of alpha. And if say alpha is like positive, then imaginary axis is gonna be somewhere behind. So I'm sorry this diagram's a little messy, but I just want to say that like these I omega naughts are not on the imaginary axis. They're on the real axis. They're on the axis of alpha naught rather. So with that being said, for positive, we have these two complex poles. So we just find the residue at them because we're enclosing them. So for that, so 1 over 2 pi. So we have 2 pi I times the sum of residues, right, for the residue theorem. Just skip all the writing it as a contour integral or whatever. Residue at s equals s1, residue s equals s2. And this, if you do all the math, turns out to be just what we started with. Tedious algebra, combine the exponentials and get the cosine back. But this is f of t for t greater than 0. For less than 0, again, as usual, piece of cake. No residue there, no pole there. This is 0. So there we go. There we go. We've recovered our function successfully. I hope that convinces you shows you the power of this theory. In the next video, I'm going to talk about some more applications. Applications to solutions to linear differential equations, Green's functions, which are a big part. And then a bunch of other things which are relevant in physics. We're going to do the properties of Laplace transforms, convolution theorem on them. If these guys are the generalization of the Fourier transform, then it makes sense, or they should have the convolution properties that a Fourier transform does. Because what if we evaluate it at real part of s equals 0? Well, then the properties have to match, right? Otherwise, all our conclusion, all our theory until now is bullshit, which is not true. But the proofs for these are going to be a little more involved, and that's why we prefer Fourier transform whenever possible, because the complex plane geometry gets hard. So see you in the next video. Hope you enjoyed it. Peace out.